Hello friends, in this video I'd like to solve the following problem from the Swiss Mathematical Olympiad, final round year 2020, problem number 1. We want to find all functions f from the set of positive integers into itself, such that f of m plus f of n divides m plus n for all positive integers m and n. So my hints for this problem: first of all, set m to be equal n and deduce that f of m must be less than or equal m. In particular, find f of 1 and then, crucially, try setting m to be 1 and n to be 1 less than a prime p, and find f of p minus 1. Then set n to be p minus 1, where p is a prime, and suppose to the contrary that f of m is strictly less than m. That should lead to some kind of contradiction for sufficiently large primes p, because remember also this obvious fact that the greatest divisor of k, apart from k itself, must be less than or equal k over 2. So give this problem a try and I will see you in just a minute. Okay, here comes my solution. As I suggested, first of all, let's set m to be equal to n. What do we have then? Then 2f of m divides 2 times m, and that obviously means that f of m divides m. But since we are dealing with positive integers, f of m must be obviously less than or equal m. It must be for every positive integer m. Because we know that every divisor of positive number is less than or equal to that number. Okay. In particular, f of 1 must be 1. Why? Because f of 1 is less than or equal 1, but at the same time, since our function goes into positive integers, it must be greater than or equal 1. So it must be exactly equal 1. Very well. Now I will set m to be 1 and n to be p minus 1, where p is an arbitrary prime number. What, however? We get the following: f of 1 plus f of p minus 1 divides 1 plus p minus 1. In other words, 1 plus f of p minus 1 divides p. Okay, but now let's take a look. We know that prime numbers have only two factors, two divisors, 1 and p itself. Well, this number is obviously greater than 1. So the only possibility is that f of p minus 1 must be equal p minus 1 for every prime number p. For every prime number p. That must be the case. Very well, and now I use this fact. Because you might be guessing that the only function which satisfies these conditions is identity. So now let's suppose to the contrary. Suppose for a moment that f of m is less than m for some positive integer n, m. Well, it cannot be greater than m because of this. So if it's not equal, it must be less than m. Set I will write it in blue as usual. So now let's set n to be p minus 1 for any prime number p, any whatsoever. And we have the following: f of m plus p minus 1 divides m plus p minus 1. And now let's take a look. This divisor is surely not is less than m plus p minus 1 because of our supposition, our assumption. And that means, as I have suggested, every divisor of some number is less than or equal this number over 2. It's my last hint. Yes, it was my last hint. That means that f of m plus p minus 1 must be necessarily less than or equal m plus p minus 1 over 2. And after some multiplications, I will have 2f of m plus 2p minus 2 is less than or equal m plus p minus 1. And that means that p is less than or equal m minus 2 times f of m plus 1. And that's a problem. Why is that a problem? Well, because we know that there are infinitely many primes. So, and m is fixed number. So it can be true for every prime that this is the case. So it's contradiction because m is fixed and there are infinitely many primes. So it's a contradiction, which can mean only one thing. F of m must be equal m for every positive integer. For every positive integer whatsoever. And that is the only possibility. Is it really a solution? Yes, it is. It's obvious that m plus n divides m plus n. So in fact, we have one and only one solution. And that's it. So thank you for watching, and I will see you next time. Goodbye.